Hey, I am Mr. Shrum, and I'm back with another tutorial for physical science. Now, last time we talked about periodic motion. We talked about Robert Hooke, Hooke's law. We looked at springs and pendulums, but now we're going to look at Newton's laws, okay? And the objective for this lesson is to understand the terms, concepts, and laws relating to force and motion. Let's get into the introduction. So, you and your friend William walk into a supermarket and grab a grocery cart. To set the cart in motion, you push against its handle. Its wheels start rolling on the floor and it moves along the aisle. When you stop the cart to take something from a shelf, the cart is at rest. This story illustrates the relationship between force and motion. Sir Isaac Newton studied scenarios like this one, to develop his theory of motion, which became the basis for the study of dynamics. That is a period of physics, a part of physics that deals with things in motion, dynamics. He built on Galileo's ideas, defined force, and wrote 3 laws of motion. In 1678, he published his laws in 3 volumes: Philosophia, Naturalis Principia Mathematica, usually just called the Principia, and is regarded as one of the most important scientific works written. Today, Newton's 3 laws of motion don't adequately explain the motion of objects at an atomic scale and at velocities close to the speed of light. But they do explain motion of ordinary objects at ordinary velocities. So Newtonian laws and physics deals with most motion. So let's get into the types of forces. A force is simply a push or a pull exerted on an object. It can change the speed or direction of motion of an object. Think about that shopping cart in the supermarket. When you push or pull on the handle of the cart, you apply a force on it. This force causes the cart to move. The movement of the cart depends on how much force you apply. The more you apply, the faster the cart moves, and the cart moves in the direction in which you apply the force. Because force has both magnitude and direction, it's a vector quantity. In the SI units, or the International System of Units, we use the magnitude of force as represented as newtons. We measure force in newtons, and that's they use a capital N to symbolize that. Forces are of 2 types: contact forces and field or fundamental forces. First, let's look at contact forces. As the name suggests, contact forces are forces that exist between objects whose surfaces touch each other. Contact forces occur because the molecules on the surface of objects touching each other interact. So contact, think of the molecules making contact with each other. So when you grip a ball in your hand, a contact force acts between your hand and the ball to keep the ball in your hand. Here's another example. If you use a rope to suspend a block, a contact force binds the block and the rope together. Types of contact forces are tension, normal force, and friction. As an example of tension, is a block suspended by a rope or a cord. Tension is the rope pulling on the block. The force of tension is transmitted from the point where the rope is attached to the block through the entire length of the rope to the opposite end. Note how tension acts away from the suspended block and parallel to the rope. Normal force, also called support force, is exerted by a surface on a stationary object. Normal force acts perpendicular to the surface and away from it. An example of normal force is a book lying on a table. The table exerts an upward normal force on the book to support the downward force of gravity. Weight is simply the force of gravity. It has the same unit of force, which is the Newton, capital N. So gravity pulls this book down, and that table, the surface, exerts a normal force in the opposite direction. Friction is the contact force exerted when two objects whose surfaces are touching each other tend to move or actually move. Friction retards or opposes motion. It slows it down. It occurs as surfaces rub against each other, causing heat energy. Friction occurs even when smooth surfaces rub against one another, because even smooth surfaces have microscopic bumps. At these bumps, the atoms of the two surfaces come close enough to form weak electrical bonds. Electrical bonds need to be broken for motion to take place. Now, we have two types of friction. They're static and kinetic. Static friction builds up when you try to move one stationary object over another. Kinetic friction is produced when an object slides or rolls on the surface of another object, which may be at rest or in motion. Kinetic friction also occurs when an object moves through a fluid. Think about that shopping cart again. The cart is at rest while you pick up a loaf of bread. When you push the cart handle to move ahead, static friction between the wheels of the cart and the floor opposes the motion of the cart. So you exert enough force to overcome the static friction and make the wheels of the cart roll on the floor. Once the cart is in motion, kinetic friction occurs. To keep the cart moving, you need to apply a force to counteract the kinetic friction. Static friction, exhibited here. Kinetic friction, exhibited here. Now, those were contact forces. Field forces, or fundamental forces, are exerted between objects that aren't touching each other. And there are 4 of these field forces. One is gravitational force. It's the weakest field, but is responsible for holding all the planets in their orbits around the sun. It is the force of attraction between any two masses. Throw any object into the air and it accelerates toward Earth's center at 9.8 meters per second squared, because it's pulled by the planet's gravitational field. The second force is the electromagnetic force. This is the force of interaction between charged particles. Like charged particles, which means this, if they have the same charge, they push away from each other. So two positively charged particles push away. But if they are differently charged, one's negative and one's positive, They are attracted to each other and pull toward each other. Electromagnetic force binds together the protons and the electrons in an atom. This force also causes magnets to attract metal objects and causes like poles of the magnets to repel each other. The third force is the strong nuclear force. This force occurs between pairs of protons or neutrons, or between a proton-neutron pair in the nucleus of an atom. Remember that protons are positively charged and neutrons are electrically neutral. So protons, positive, neutrons, neutral. The two particles form the nucleus of an atom and are collectively called nucleons. Because there is a strong nuclear force between the particles, they do not repel each other, despite the electromagnetic force that exists between them. Nuclear force is responsible for holding an atom together. So we have gravitational force, electromagnetic force, strong nuclear force, and then there's a weak nuclear force. This force exists between subatomic particles in the nucleus, but it's not as strong as the strong nuclear force. So we call it the weak nuclear force. But it still has observable consequences. Beta decay, the emission of high energy electrons from the nucleus, is an effect of that weak nuclear force. So now we're going to label each as either contact or field. Contact means they have to be touching one another for it to work, and then field force is that is not necessary. They don't have to be touching. So we just talked about gravitational force, electromagnetic force, and yeah, those are the field forces. And then frictional force is contact, normal force is contact, tension, contact. Bam. All right, moving on. Newton's laws. So, like the grocery cart example again, if you let go of the handle as you're pushing a cart, the cart still moves along the aisle for a short time, and then it might stop. This behavior is due to the property of inertia. Inertia is the natural tendency of an object to resist any change in its state of motion. Galileo was the first scientist to define inertia. He said that inertia causes a moving object to remain in motion as long as no external force acts on it. Newton's first law of motion extends Galileo's theory and states the following. Every object continues in its state of rest or state of uniform motion in a straight line unless acted upon by a non-zero net force. And that means if an object is rest, it wants to stay at rest. If it's in motion, the object stays in that motion unless acted upon by another force. So with the shopping cart, it's at rest at first. It remains at rest until you push it, until you apply a force. When you push the cart, it moves in the direction in which it is pulled or pushed. Even when you let go, the cart keeps moving at constant velocity along a straight line path because inertia causes the cart to retain its state of motion. Or as the law puts it, the cart continues in its state of uniform motion in a straight line. So now we're going to look at why the cart stops after moving a short distance down the aisle. According to Newton's first law, the shopping cart would continue to move at a constant speed in a straight line along the aisle as long as the net force acting on it is zero. Now, net force, what does that mean? That's just the vector sum of all the forces acting on an object. The addition of all forces is mathematically denoted by the summation symbol, this symbol. That just means we're adding up anything that follows. If you let go of the cart's handle, you're no longer applying a force on it. However, a force does exist between the wheels and the floor, and that force is the friction force. So there is a non-zero net force acting on the cart. Remember that friction acts in the direction opposite of the cart's motion. That makes the cart gradually slow down and then stop. So here you're pushing it forward, you let go, but then friction is the only force acting on it, and that leads it to stop. If the net force acting on an object is zero, the object is said to be in equilibrium. The state of equilibrium is represented by this equation. The summation of forces equals zero. Now assume the two forces F1 and F2 are exerted on an object. Then the net force acting on an object would be the summation of forces equals F1 plus F2. For the object to be in equilibrium, we have to have F1 plus F2 equals zero. So if these two forces are in equilibrium, that F1 has to be negative F2. That means that force is acting in the opposite direction as the first force. And they have to be equal in magnitude and opposite in direction for the object to be in equilibrium. If only one force is exerted on the object, the net force acting on it would not be zero, and the object would not be in equilibrium. In other words, at least two forces must act on an object for it to be in equilibrium. It follows from Newton's first law of motion that an object in equilibrium retains its state of motion. To change the object's state of motion, its equilibrium must be disturbed so that a non-zero net force acts on it. According to Newton's first law of motion, there are two forms of equilibrium, static and dynamic. An object at rest is in static equilibrium. An object moving at a constant speed in a straight line path is in dynamic equilibrium. So static as in nothing's moving. There's no motion really. But if it's moving at a constant speed in a straight line, it's moving, but it's still in equilibrium. That's what dynamic equilibrium means. So picture a book lying on a table. You have that gravitational force, but the equal and opposite normal force by the table. Thus, it's steady and in static equilibrium. Because it remains at rest, it is in a static equilibrium state. The net force equals zero because this force pushing down equals the force pushing up. Now, dynamic equilibrium. We're going to use this cart throughout the entire lesson, so get ready. As it moves, there are two forces applied. You're applying one force to push it forward, and then there's the friction acting in the opposite direction. If the two forces are equal and opposite, they will cancel each other out, and the net force acting on the cart will be 0. So the cart will move at a constant speed in a straight line path along the aisle. And that is dynamic equilibrium. So now we have a question. Stephen pushes a crate across a warehouse floor. If the crate moves at a constant speed in a straight line path, which statement is true according to Newton's first law of motion? The force that Stephen applies is greater than the force of friction between the crate and the warehouse floor. Well, no, because if it's moving at a constant speed, that would mean they're equal. It's in dynamic equilibrium. So that means the net force is 0. If it's moving at a constant speed in a straight line, dynamic equilibrium. And that means it's moving, but the net force acting on it is 0. Another question. A block of wood is in static equilibrium. Which statement is true according to Newton's first law of motion? Oh, sorry. It's at rest. This would have been correct if it said in the opposite direction. So one force is acting and the other is acting in the opposite direction. You got to be careful reading these questions because some of the wording affects the answer. But yeah, that should have been obvious. Static equilibrium means it's at rest. This one's wrong because the forces are equal, they're just opposite. The net force is 0. This one's saying it's non-zero, so that doesn't make any sense. And then this says they're both going in the same direction, and that doesn't make any sense either. So the correct answer is at rest. So now back with the shopping cart. You need to push a shopping cart more when you add groceries to the cart. When it's empty, it's a little easier to push around. However, the groceries pile up in the cart and you need to apply a stronger push to move the cart. Because now it's offering greater resistance to a change in its state of motion. Recall that an object's tendency to resist a change in its state of motion is inertia. So a cart filled with groceries possesses more inertia than an empty cart. That means that the inertia of an object depends on the quantity of matter in the object. This quantity is called mass. Think of mass as a measure of the inertia of an object. Now, the SI unit for measuring mass is kilogram. However, in the US, the mass of an object is commonly translated into pounds, which is technically a measure of weight and not mass. Mass and weight are often confused and used interchangeably, but they're not quite the same. Weight is the gravitational force that an object experiences. Mass is the quantity of matter in an object. The magnitude of the weight of an object is given by the equation weight equals mass times the gravitational force, where m is the mass of the object and g is a symbol used to represent gravity's acceleration, or the acceleration due to gravity. So take this example. There's a block of wood with a mass of 1 kilogram. G equals 9.8 meters per second squared near Earth's surface. So the weight is just mass times the acceleration due to gravity, 1 times 9.8. And that gives you newtons. Remember that the SI unit for measuring the magnitude of a force is Newton. A block of mass 1 kilogram weighs 9.8 newtons on Earth's surface. This weight is about 2.2 pounds. In other words, 1 kilogram block weighs 2.2 pounds on Earth's surface. Now assume that the block is weighed on the moon's surface, where the gravitational force is 1/6 of that on Earth's surface. The block would weigh just 1.6 newtons on the moon's surface. So the weight of an object changes depending on the surrounding gravitational field, but the mass is constant. So how can we relate that back to the cart? When you push the cart, the force causes it to move, meaning there's a change in its velocity. Recall that acceleration is defined as the rate of change in velocity. So you can say that the cart accelerates down the aisle. If the force you're applying remains constant, you'll observe that the cart moves more slowly as you fill it up with groceries. So another way to put that is the cart moves faster when it is empty than when it is loaded with groceries. So the cart's acceleration is inversely proportional to its mass. So we can write that as A is inversely proportional to mass, or 1 over mass. And how can you relate acceleration to that net force acting on the shopping cart? So picture you've loaded it with groceries and you're finding it difficult to push the cart down the aisle. You ask your friend, William, to help you push the cart. When the two of you push the cart, it moves faster down the aisle than it does when you push the cart alone. It moves faster because the net force acting on the cart increases. In other words, the cart's acceleration increases with an increase in net force. Now, assume that instead of pushing the cart, William pulls it. He exerts a force in the opposite direction to the force you're applying. That counteracts your force on the cart and changes the net force. So the cart moves more slowly, stops, and even reverses direction. The acceleration of the cart changes as the net force acting on it changes. If your push on the cart is greater than the pull William exerts on it, the cart will move in the direction of your push. If William's pull is greater, it will move in the opposite direction. So the cart's acceleration is directly proportional to and in the direction of the net force acting on the cart. Mathematically, that means A is directly proportional to the sum of the net forces. Newton formally expressed the two correlations you've just seen in his second law of motion. According to this second law, the acceleration is directly proportional to the net force acting on it in the direction of that net force and inversely proportional to its mass. So mathematically, we can say A is directly proportional to the sum of the net forces and inversely proportional to the mass. So if all quantities are specified in SI units, Newton's second law can be written as Acceleration equals the sum of forces divided by mass. Or if you rearrange that, you get the sum of forces equals mass times acceleration. F equals ma, a very important equation. Force equals mass times acceleration. So we're given a question. Paul is pushing a wheelbarrow in his garden to the east. His friend John comes along and starts pushing it in the opposite direction, to the west, with a force that's twice as great as Paul's. What can you say about the motion of the wheelbarrow? Well, if he's pushing it to the east, and then his friend comes over and starts pushing it to the west, and he's using a force twice as great as Paul's, well, it's going to go in the direction of John, since his force is greater. And that means it's going to move to the west. Yay. So at the start, I'll just summarize everything here. At the start, the force was defined as any push or pull exerted on an object. However, a push or pull is never exerted in isolation. For example, when you push against the handle of a loaded shopping cart, your hand is pressed at the place where it touches the handle because the handle exerts a push on your hand. And when you pull a loaded suitcase, your fingers move back a little because the suitcase exerts a pull on you. In both examples, one object interacts with another. Each interaction involves a pair of opposing forces. The two forces occur simultaneously, and one can't exist without the other one. However, you can't tell which object in an interaction applies force and which object receives it. So Newton said that both objects must be treated equally, which he states in his third law of motion. Newton's third law of motion states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. If you call one of the forces action and the other reaction, you can restate that in this way. To every action, there is an equal and opposite reaction. There's a little summary video. Oh, here's a summary. Force is a simple push or pull exerted on an object that can change the direction and speed of an object. There are two types of forces, contact and field. Contact forces act between objects that are touching each other. Tension, friction, and normal force are types of contact forces. Field forces act between objects that are not touching each other. Think of gravitational force, electromagnetic force, strong and weak nuclear forces. And those are the four types of field forces. Sir Isaac Newton, in the mid-1600s, formulated 3 laws of motion. The first law states that an object continues in its state of rest or uniform motion in a straight line unless an external non-zero force acts on it. The object resists any change in its state of rest or uniform straight line motion. This is the law of inertia. If an external unbalanced force acts on an object, the object starts accelerating. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. Newton's third law states that when one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So the first law means that the object doesn't want to change its state if it's in rest or if it's moving at constant speed. The first law is the law of inertia. The second law states that F equals ma. The net force equals mass times the acceleration of an object. And then the third law is for each action, there is an equal and opposite reaction. I hope that was helpful, and I will see you guys in the next lesson. See ya.